In just a few weeks of conflict, a sea passage less than 33 kilometers wide managed to squeeze nearly 20% of the world's oil flow. That places the Strait of Hormuz, the most critical energy corridor on Earth, where more than 20 million barrels of oil pass through every day to keep industries running from Asia to Europe. But the real epicenter of the panic does not lie only in this narrow choke point. It lies in the massive machine being blocked behind it, Ras Tanura. Far beyond the idea of a typical export terminal, this mega infrastructure is essentially the largest steel master valve of the global energy system. A super export hub where up to 6.5 million barrels of oil per day are pumped directly from deep beneath the Saudi desert and loaded straight into some of the largest oil tankers on the planet. Let's join Mandarin Tech to explore the energy heart of the modern world. If the surface of the ocean is an open transportation network, then Strait of Hormuz is the most brutal spatial trap in the global energy system. On a map, it looks like nothing more than a narrow water passage between Iran and Oman. But in reality, for major energy powers such as Saudi Arabia, Iraq, Kuwait, and the UAE, this is the only gateway through which their black gold can reach the world. The dominance of Hormuz has worried Gulf countries so deeply that they have been willing to spend billions of dollars just to create an escape route. The clearest example is the 380-kilometer ADCOP pipeline, worth about $4.2 billion US, built by the UAE across the desert to bypass this shipping route. Engineers even once proposed an extraordinary idea, blasting through millions of tons of limestone and cutting across the 2,000-meter-high Hajar Mountains to build the Musandam Canal, creating an alternative outlet to the open sea. But all these technical efforts proved ineffective. The billion-dollar pipeline can carry less than 1/10 of the total flow, while the mountain-cutting canal has remained only a concept on paper. This reality confirms a harsh geopolitical principle. Hormuz is a bottleneck that cannot be broken, and no man-made mega-infrastructure on Earth can truly replace it. And the worst-case scenario is unfolding right now. Since late February 2026, military tensions between Iran and the coalition led by the United States have turned the Strait of Hormuz into one of the most dangerous hotspots in the world. After airstrikes targeting Iran's anti-ship missile systems near the strait, Tehran responded by warning that it could close the shipping route and by deploying military measures to control maritime traffic. Within just a few days, oil tanker traffic through Hormuz dropped by more than 90%. Hundreds of vessels were forced to wait outside the Gulf, and many major shipping companies temporarily suspended operations due to security risks. Missile responses, drone activity, and warnings of possible attacks on commercial ships push the maritime corridor that carries about 20% of the world's oil supply into a state of partial paralysis. As a result, oil prices rose above $100 per barrel, marine insurance costs increased several times over, and energy supply chains from Europe to East Asia began to face clear pressure. In this situation, the world has begun to recognize a troubling reality. When Hormuz becomes unstable, no economy remains safe. And behind that narrow bottleneck, where some of the largest oil reserves on the planet are concentrated, the entire Gulf export system is also starting to face an unprecedented logistics crisis, with the central focus being Ras Tanura port. Hidden along the eastern coast of Saudi Arabia and facing directly toward the Persian Gulf, Ras Tanura port is not simply a seaport. It is the largest oil export terminal on the planet, where millions of barrels of crude oil from massive desert oil fields are gathered, pressurized, and pumped straight into the ocean every day to sustain global industry. Beyond that, it is a vast coastal industrial complex directly connected to a trans-desert pipeline network stretching thousands of kilometers, ultra-high-pressure pumping stations, enormous storage tank farms, and offshore loading piers capable of receiving some of the largest oil tankers ever built. From here, supertankers of the VLCC class can carry up to 2 million barrels of oil per voyage as they depart the port and head toward major consumption centers across Asia, Europe, and North America. In 1939, construction of the first pier structures at Ras Tanura port officially began. However, before the access bridge could extend toward the offshore loading area, engineers first had to build a protective offshore breakwater. At that time, the eastern coast of Saudi Arabia lay on a shallow seabed covered with thick layers of soft sediment, frequently disturbed by seasonal winds and waves in the Persian Gulf. Without a protective barrier, large oil tankers could not safely approach the loading zone. As a result, a multi-layer rock-fill breakwater was selected as the most suitable solution for the offshore construction conditions of that period. The breakwater was built by placing a core layer of dumped rock using barges, followed by larger rock layers to improve slope stability. An outer layer of heavy armor stones, installed by floating cranes, helped dissipate wave energy and reduce seabed scour. At the same time, the navigation channel was dredged to provide sufficient depth for safe tanker access. As soon as the water inside the breakwater became stable enough for offshore construction, engineers at Ras Tanura port began building a key structure, the oil export causeway extending out to sea. This causeway created a direct connection between the onshore pipeline network and the offshore tanker loading area. The main challenge came from the seabed conditions along the eastern coast of Saudi Arabia, where thick layers of soft marine clay made it impossible to place structures directly on the seabed, like at typical deepwater ports. Instead, the causeway was supported by large steel pipe piles driven deep into stronger load-bearing layers beneath the seabed using offshore construction barges. After the foundation system was completed, steel girders and connecting frames were installed span by span, forming a long technical corridor from the shoreline to the offshore loading zone, allowing crude oil to be transported directly from inland desert fields to large tankers waiting offshore. By the mid-1950s, crude oil exports through Ras Tanura port increased rapidly, and the North Pier was no longer able to meet operational demand. At the same time, the arrival of new generations of oil tankers with deeper drafts required loading infrastructure to extend farther into deeper offshore waters. In response, Saudi Aramco began constructing the South Pier as a dedicated offshore loading complex designed for large-capacity tankers. Unlike the nearshore causeway structures, the South Pier was engineered to withstand much higher mooring forces and vessel impact loads. Its foundation system used large-diameter steel pipe piles, driven deeper and arranged at higher density to ensure stability under wave and wind conditions typical of the shallow Gulf waters. Mooring dolphins and breasting dolphins were positioned separately from the main platform to reduce direct structural loads during berthing and tidal movement. Multi-joint marine loading arms were installed on the offshore platforms to connect directly with tankers, allowing high-volume pumping while accommodating vessel motion. At the same time, the offshore approach channel was dredged in seabed elevations, adjusted to ensure safe access for large tankers under different tidal conditions. As the number of oil tankers increased rapidly with rising global energy demand, a single loading area was no longer sufficient to maintain continuous flow at Ras Tanura port. The problem was not simply expanding one large terminal, but creating multiple offshore loading points operating in parallel in the Persian Gulf. To solve this bottleneck, Saudi Aramco developed the Sea Islands complex as independent export points, allowing multiple oil tankers to operate at the same time without interrupting flow. The Sea Islands were formed by dredging and pumping sand from the seabed to create artificial offshore land masses, then reinforced with rock layers to stabilize their shape and prevent erosion. Beneath these islands, large-diameter steel pipe piles were driven deep into load-bearing layers to support the entire loading platform structure. The system was divided into breasting dolphins, mooring dolphins, and loading platforms to distribute the forces generated when multiple tankers operate simultaneously. On the loading platforms, multi-joint marine loading arms maintain stable connections under wave and tidal movement, ensuring that oil flow remains uninterrupted during operations. At the same time as expanding its offshore loading points, Saudi Aramco constructed a massive crude oil storage complex behind the port terminal to ensure continuous export flow management. The cylindrical steel storage tanks typically have diameters ranging from about 60 to more than 100 meters, with each tank capable of holding between 500,000 and 1 million barrels of crude oil. These tanks are arranged in a network directly connected to the central pipeline system. The tank foundations are reinforced with compacted sand bedding layers and circular concrete ring foundations to evenly distribute the enormous loads generated by the stored oil. The tank shells are assembled using a staged plate lifting method, allowing fast and accurate construction under the harsh coastal desert climate conditions. Above each tank, floating roofs are installed to reduce oil evaporation and minimize fire and explosion risks, ensuring safe operation for the entire large-scale storage system capable of holding tens of millions of barrels at Ras Tanura port. To transport crude oil from the onshore storage tank area to the offshore loading complex at Sea Islands, Saudi Aramco constructed a large-scale subsea pressure pipeline system that serves as the main transmission route of the entire export hub at Ras Tanura port. This system allows millions of barrels of crude oil per day to be transported directly from onshore processing facilities to offshore loading points serving very large crude carriers. The pipelines are made from large-diameter, thick-walled steel pipes designed for long-term operation under high-pressure conditions and in highly corrosive seawater environments. Before installation, individual pipe sections were continuously welded together on specialized pipe-laying barges and then inspected using ultrasonic testing to ensure sealing integrity and structural strength. The outer surface of the pipelines was coated with concrete weight coating to increase stability and keep the pipeline securely positioned on the seabed. During installation, the pipeline was continuously lowered from the laying barge through a curved support structure that controlled the bending radius, helping reduce stress as the pipe made contact with the seabed. Prior to installation, a trench was prepared along the pipeline route to protect it from ship anchors and seabed currents. After placement was completed, the pipeline was backfilled with protective material, forming a stable energy transport corridor between the shoreline and the offshore export terminal complex. To reach black gold, engineers operate massive drilling rigs that penetrate several kilometers deep beneath the deserts of eastern Saudi Arabia. After each drilling stage, steel casing pipes are lowered and special cement is pumped into place to strengthen the well walls, creating a stable production corridor through high-pressure geological layers. Few people realize that the oil exported through Ras Tanura port actually begins its journey deep underground in giant fields such as Gawar and Abqaiq. Here, oil does not exist as large underground lakes as many imagine. Instead, it is trapped inside tiny pores within reservoir rock, similar to water held in a sponge. After the wells are completed, oil flows to the surface using natural reservoir pressure or enhanced recovery methods such as water, gas, or steam injection to maintain stable production. Even with modern technology, typically only about 30 to 40% of a field's total reserves can be recovered. From the production wells, crude oil is transported to primary processing centers where gas and water are separated, then sent through pipeline networks stretching thousands of kilometers across the desert toward Ras Tanura. There, massive storage tanks act as logistics buffers before export. Finally, high-pressure pumping stations push the oil to offshore loading terminals, such as South Pier and Sea Islands, where VLCC tankers receive millions of barrels per loading cycle, supplying energy to East Asia, Europe, and North America. In the global energy industry, not every country with oil holds the same level of power. Real energy power belongs to countries that not only have massive reserves, but also the ability to deliver that oil to international markets every day at an industrial scale. Saudi Arabia is one of the few countries that meets both conditions. Today, the countries with the world's largest oil reserves include Venezuela, Saudi Arabia, Canada, Iran, and Iraq. Among them, Saudi Arabia stands out for maintaining stable export capacity for decades. The giant Gawar oil field alone has produced millions of barrels per day for generations. However, reserves only become real power when they can be transported continuously to global markets. To make this possible, Saudi Arabia built a vast energy logistics network, including thousands of kilometers of desert pipelines. Major processing centers such as Abqaiq, and especially Ras Tanura port, the country's main oil export gateway. Ras Tanura handles about 90% of Saudi Arabia's hydrocarbon exports and can ship roughly 6.5 to 9 million barrels per day. Its strategic location is also close to the Strait of Hormuz, where around 20 million barrels of oil, about 1/5 of global supply, pass each day. Because of this, Ras Tanura is not just a coastal terminal, but a critical junction linking desert oil reserves, cross-desert pipelines, and one of the world's most important maritime energy routes. From drilling wells thousands of meters deep beneath the desert to the offshore sea islands in the Persian Gulf, the Ras Tanura megaport represents one of the highest achievements of global energy logistics engineering. It is not just a massive oil export terminal, but a critical control valve that helps keep many industries around the world running every day. However, there is a paradox. An infrastructure system with global influence still depends on a very fragile geopolitical corridor. Because of this, Ras Tanura is both a symbol of oil power and a clear reflection of how vulnerable the modern global energy system can be. Thank you for watching Mandarin Tech today. If you found this video interesting, please like and follow the channel to explore more impressive mega projects from around the world.